welcome to another class of W211. In today's class, we will discuss about the most famous laws of electrical engineering, and these are the Ohm's law and the Kirchhoff's law. So let us start and see what is Ohm's law. Ohm's law was discovered back in 1827 by a guy whose name was Georg Simon Ohm, and he in 1827 published a paper in which he explained that in a wire or in a material having the resistance R, there exists a linear relationship between the applied voltage and the flow of current. So what he proposed was that if we have some conductor like this with some cross sectional area here, and if we apply the voltage here, as a result the current starts to flow in this particular direction where this is the applied voltage. It has an area A and it has a length L. Then according to Georg Simon Ohms, he stated that the current that will flow as a result of the application of the voltage across the two terminals of a wire element, that current I is equal to A V over rho into L. If you see here, this A represents the cross sectional area of the wire, this rho shows the resistivity of the material, and this L represents the length of the conductor. Georg Simon Ohms actually established that there exists a linear relationship between the applied voltage and the current, provided that we have the temperature constant. But you see, this particular equation has this A, this whole part A, rho and L. This is all the property of the material. So different materials have different properties. For instance, we may have a different resistivity for a copper wire, we may have a different resistivity for the aluminum, and so on and so forth. But you see, in terms of the electrical circuits, most of these properties are material dependent, and it is always desired to express the relation of the current and the voltage in terms of some value that is known as the resistance. So what he concluded here, that we say that the resistance R of any material is equal to rho L over A, and that makes sense because larger the cross sectional area of any current carrying conductor, the lesser will be the resistance of that element. Resistivity rho depends on the material and the length. So in terms of these two parameters, he proposed that the voltage applied is proportional to the current, provided that the resistance stays constant, and that is at a constant temperature. So one thing that is very much crucial for the validation of Ohm's law, it is that the experiment in which you are trying to establish that there exists a linear relationship between the voltage and the current, it should be at a constant temperature. So if I say that I have some voltage applied here, and I have a resistance here R, right, and we say this R is 10 ohm. So this ohm, named after the scientist, it is the symbol of the resistance, and we say that we want to find out the current which is flowing in this particular circuit, that is I is equal to V over R. Now if we plot the characteristics of the current versus the voltage, then there exists a linear relationship, and that linear relationship between the current and the voltage, right? But this linear relationship, as I said earlier, is actually temperature dependent. Suppose that we have a resistance which changes with time. For instance, we have electrical bulb available, electrical bulb, commonly known as an incandescent bulb, something around a few watt rating. They're available and they're widely used for illumination. These electric bulbs have a resistance which is different when they are operating than when they're operating and when they're not operating. So suppose that we have a resistance R, that is something around 10 ohm, when they are turned off. So they have some resistance R equal to 10 ohm, and when we turn them on, the resistance shoots up to 50 ohm, and there it gets stabilized. And under these circumstances, if you see, then the current will no longer be a constant current here. So if this is the current I, then this current will no longer be a constant current unless and until the resistance sets at this particular point at 50 ohm. So it may happen that when you turn on this particular supply, suppose that we have a switch here, if you turn on this particular supply and this resistance is equal to 10 ohm, then at that particular time the resistance will shall start from this particular point, and it will come back and it will become stable at whatever the value according to this 50 ohm is. So you see here that this particular point during which the temperature of the electrical bulb was changing and hence the resistance was actually increasing, there exists a non-linear relation here, which means that the Ohm's law is no longer applicable under the circumstances where the temperature is not constant. So this is the first thing that we should remember, while studying this Ohm's law, that V is equal to I into R only holds true at constant temperature. If the temperature is changing, then this Ohm's law is no longer applicable. Going forward, we say that the that those material properties, they can be attributed in terms of the resistance R, and hence it can be attributed in terms of this type of a symbol. And then we have in terms of the graphical of the symbol that we use in the text to represent the values, we use this ohms or the omega sign. Now the question arises is, what is an ideal resistance? An ideal resistance has three properties. Let us say what is an ideal resistance. An ideal resistance has three properties. Number one, it is a two terminal device, and this is one of the properties that we studied during the basic circuit element property. This is one of those properties that it holds true that it should be a two terminal device. The second thing here is that it is bilateral. What do we mean by this bilateral property? This means that if the voltage polarity is changed, then the current will also change the direction. What I mean to say here is that a resistance allows the flow of current to flow either from this terminal A to B or from terminal number B to terminal number A. There are some certain devices in electrical engineering that do not allow a bidirectional flow of current through them. For example, we have a diode here. Diode is not a bilateral device because current can only flow from anode to cathode, and there is no flow of current ideally from the cathode to the anode. And even in the practical cases, this current is a way lesser current than the forward current of a particular diode. So the second property of the resistance is that it is actually a bilateral device. And the third property here is for this resistance that it is constant, right? It is constant. What does this mean? This means that the resistance is actually a linear time invariant device. There is no effect of the temperature its value. There is no effect of the time on its value. It's a linear time invariant device. Or in short terms, an ideal resistance is a resistance which obeys Ohm's law, or which holds the Ohm's law regardless of the operating temperatures and regarding of the applied voltage and the current. Its value stays constant. So these are some of the properties of an ideal resistance. Moving forward, Ohm's law is V is equal to I into R. And in the previous class, we have studied that power is a product of voltage and the current. So P is equal to V into I. This means that if we substitute the value of V in this particular power expression, then we have I square into R. This means that if we have some resistance available and we know what is the current flowing through that particular resistance R, then we can find out the power of consumed by that particular resistance without knowing what is the voltage across this resistance. Similarly, I can say that I is equal to V over R, and if I substitute the value of this I into this power expression, I will get power is equal to V square over R. All of these three expressions give us the value of the power which is dissipated across a particular resistance. Now, important point here is that why we need to specify the power dissipation across a particular resistance. Now, if you see that the resistances that you use in your laboratory experiments, they are somehow thinner and they have a maximum power carrying power dissipation capacity of quarter watt, right? So most laboratory resistances are 1 by 4 watt rating. What does this mean? This means that even if you use a resistance of 1 ohm or you use a resistance of 100 ohm or any other value, the maximum power that they can actually dissipate without burning out or without failing is equal to 1.1 is equal to 0.25 watt. So if there is a power dissipation greater than the power dissipation capability of those resistances, they will simply fail. So again, we conclude that the resistance is attributed in terms of the ohms, or we say what is the value of this resistance, and the second one is in terms of the power rating. So without the power rating, it is good to solve the circuits on paper, but practically it is not feasible to install a resistance without specifying the power rating of that particular resistance value. So if I say that I need if I say that for some particular device we need 100 ohm resistance, then we also have to specify what is the power rating of that resistance. Otherwise, installing a 100 ohm quarter watt resistance to a place where the power dissipation is more than quarter watt, the circuit will simply fail practically, although it will give you very nice result on paper while you are solving that particular thing. For example, I have 10 volts here. This is the voltage, and I apply it to a resistance equal to 5 ohm. This means that there will be some current that will flow through this particular circuit. Now, if I say what is the current here, I is equal to V over R, and that is equal to 2 ampere. But what about the power rating of this particular resistance? The power rating required here is P is equal to V into I, and that is equal to 20 watt, right? That is equal to 20 watt, and the same thing can be calculated by multiplying the I square by R. So this is 4 times 5, that also gives me 20 watt. Now if I use a 5 ohm resistance of quarter watt, that is normally used in the laboratory experiments of W211 or the linear circuit analysis course, then it will simply burn, because it is not capable of dissipating this much amount of power, and its power carrying capacity is merely 0.25 watt. What does this mean? What is the solution for that? The solution is to use the resistances that are known as power resistances. Let me show you some of the power resistances here. So you see this particular power resistance is a 100 watt power resistance, and it comes in a quite a big metallic frame. And then we have some small resistances value available here. So you see that there are some resistances which are thin, and some which have a more cross sectional area. All the resistances, if they are assumed to be having the same particular value, yet they are actually classified in terms of their power rating. So you cannot use this small particular resistance on an application where the power rating is more than quarter watt. Thank you very much. Stay safe.